Hi everybody. So let's work a real quick example problem. Tack on the end of the last lecture. This is going to be a Carnot refrigerator. So I've got a Carnot refrigerator. We're given some information about this refrigerator. We're given that so if we draw the refrigerator real quickly here, I've got a compressor putting a work input, or in this case a power input. And so the compressor then is going to feed a condenser unit. Condenser unit's going to lose heat to a high temperature source. Down here I've got an evaporator. The evaporator is going to remove heat from a low temperature source. And then, so it's going to be, we're going to have high pressure in the condenser side. We're going to drop the pressure across some kind of an expansion valve. You can put a turbine in here, by the way, and get a little bit of work out. In really large refrigeration, industrial size refrigeration systems, you can actually have a turbine in here extracting some power. You're not going to put that in a small refrigerator. It's just too many moving parts. It's too likely to fail. But what we can do is just put an expansion valve in here. And what that does is it will drop the pressure on the other side of, so I've got high pressure here, low pressure there. And once the pressure drops, also the temperature will drop. So if I've got a high pressure liquid or high pressure liquid vapor mixture and I allow it to expand, it's going to come out on the lower pressure side actually as a very low temperature vapor or low temperature liquid vapor mixture. Run it through the evaporator. Make sure then we have complete vapor coming out, low pressure vapor coming out, going back into the compressor unit. Right, so we've talked about a refrigerator before. That's probably too much detail. So we've got a hot temperature space, and given to us is that it's the hot temperature space is 25 degrees C. The power input to the compressor unit, they're saying, is 500 watts. And they're telling us that the coefficient of performance for this refrigerator is 4.5. They want us to find, so this is, since this is a W dot, I'm going to call this a Q dot H and a Q dot L, and TL is my cold body down here. And what the problem wants us to find, it wants us to find both Q dot L. It says determine the rate at which heat is being removed from the refrigerated space, and then also determine the temperature of the refrigerated space. Okay, well, we can do that. I think we've got, they've also told us that it is Carnot, therefore it is a reversible cycle. So Carnot, by definition, is a reversible cycle. They could tell us it's a reversible refrigerator and get the same result. So we want to find this Q dot L and TL. Well, if we look at the entire refrigerator and we do first law for the fridge, if you will, for the refrigerator. First law for the refrigerator says, well, I've got a power input. I'm putting in Q dot L, so both those are going to be added. I'm removing Q dot H, so that's a negative, and it's a cyclic system, so that's just going to all add up to be 0. So if I need Q dot L, I could find that through, let's see, Q dot H minus the power input. Now I know the power input, but I don't know Q dot H. Now if I knew the exit and entrance conditions on the condenser, I could find Q dot H and we'd be done, but I don't know those. And that's a common thing. They'll tell you maybe the pressure and temperature or the pressure in saturated liquid or something. They'll tell you properties of the condenser. We don't know those in this case, so we're going to have some other way to get Q dot H. But we do know something else. They've told us the coefficient of performance for this refrigerator, and because it's a Carnot, we can also put this reversible subscript on here. Now, the coefficient of performance for any refrigerator is always going to be what you want divided by what you have to do. Well, what we want in a refrigerator is Q dot L. To get it, we're going to have to put in a little bit of work, some power input. Now, if I take this and substitute, well, we did this earlier. We said power. We did this in a previous lecture. We said, well, the power input is equal to QH minus QL. I'm going to use that, plug in down here, and modify this equation. So this simplifies down to 1 over Q dot H over Q dot L minus 1. Right? Well, I know the COP. That was given to me. They said it's 4.5. So I know this quantity. I can use this to find Q dot L, or I can use it to find Q dot H, and or I can use it to find any of those. Now, because it's a reversible refrigerator, because it's a Carnot device, Carnot is reversible by definition, that means it's operating at its maximum output, its maximum performance, or its maximum efficiency. So because that's the case, we can also say that the ratio of the heat transfer is equal to 1 over the ratio of temperatures. So remember, the problem asked for the low temperature. Given the high temperature, I can also find that here. Okay, so this one's not too bad, right? Most of these chapter 6 for us problems, the chapter 6 for us, or a similar chapter in another textbook, most of them are pretty straightforward problems. What's your device? What are the performances? What's the efficiency or the coefficient of performance? Is it a reversible device? Then some different rules apply. Specifically, if it's a reversible device, the temperatures of these two bodies are the only things that control the performance or the efficiency. And that's the case here. So let's find the two quantities we want to know. We want to find Q dot L. That's not too bad. To find Q dot L, I'm going to solve this expression here set equal to 4.5. So Q dot L is equal to 4.5 times the power input, which is a known quantity. We said the power input is 500 watts. So it's 4.5 times 500 watts. Let's see if I can maybe even do that in my head. I don't know if I'm going to have to pull a calculator here out or not. Let's see. 4 times 500 is 2,000. And then 5 times 500 is 25. So that's 6,500 watts. Does that look right? Yeah? Okay. There's one answer. The other answer I don't think is going to be too bad. We're just going to say that the COP for the refrigerator, and because it is a Carnot, we can use the reversible COP, which that is 1 over TH over TL minus 1. Right? So both of these, this one and this one, these are always true for any refrigerator. This expression is only true if it's a reversible refrigerator. So we have to make sure we know that. Did they tell me it's a reversible refrigerator, or if they told me in this case it's a Carnot refrigerator, that's a given. So we're trying to find TL. We know TH, we know COP, we're trying to find TL now. So do your algebra however you like. Okay with that? All right. I think that's right. Let's see here. I want TL, so I'm going to take TH. I'm sure there's a simpler way to do this, and I don't care. I'm going to do it the hard way. That's +1. Right? Okay. TH. What is TH? It is not 25 degrees C. Right? Do not use Celsius or Fahrenheit when you're multiplying or dividing by temperatures. Period. You have to use Kelvin. When in doubt, use Kelvin. What is that? 298 kelvins. Okay? 298 kelvins over 1 over 4.5 plus 1. Okay? We could do some fractions here if you like. This is basically, this is 2 over 9 plus 1. 298 kelvins divided by, so this is 2/9 plus 9 over 9, so it's 11/9 if you like. So I think that's right. TL would be 298 Kelvin times 9 over 11. I think that's right. I don't know. Let's see. Let's just go back here and we'll just do it. We'll do it from right here and make sure. Right? 1 over 4.5 plus 1. We're going to invert that. Multiply 298 by that value. I'm getting down here 243.8. I erased it. Let's see if I was right. 298 times 9 divided by 11. Yeah. 243.81. Those are kelvins. Or about minus 29 point, 0.2, we'll say, degrees Celsius. Okay, and let's check these numbers up here. I don't think this is right. I don't think it's right at all. 4.5 times 500, since I got my calculator out. No, that is not right. That's silly me. I moved a decimal place. It was 2,000 plus 250, not 2,000 plus 2,500. So it's 2,000 plus 250. Got carried away with my decimal places there. Okay. So Q dot L, it teaches me to do it in my head, right? Q dot L, 2250, and temperature of the cold space, about minus 22 or minus 29 degrees C. All right, guys. Let me know if you have questions. Shoot me an email, leave me a comment, find me in Canvas, and let's keep going. Loud pop here.